Welcome to Chemistry Lover, and this is the first part of the infrared spectroscopy. So in the introduction video of the absorption spectroscopy, I told you about all kind of spectroscopy which we are going to discuss, and this is the first video which is on the infrared spectroscopy, or which we in short we call IR spectroscopy, and this is also a kind of absorption spectroscopy. So this course will be important for BSc, MSc, IIT JAM, GATE and csir-net exam, and I will discuss infrared spectroscopy in two parts. This is part 1 and there will be another part which is part 2. So in the part 1 I will basically develop the basic principles and how the overall thing works and what is the overall picture of the IR spectroscopy, and in the second part of this series or of IR spectroscopy I will discuss about some specific examples which are important for the exam. So let us first begin. So what is IR spectroscopy? IR spectroscopy deals with chemical bonds like carbonyl, nitro, then CH, C triple bond N, C triple bond C, all these things. Okay, so NMR and other spectroscopy, they deals with the property of atom, whereas IR spectroscopy deals with property of bonds. It is not related to single atom, but it is related to bond, and that's why we get important information about a functional group from IR data. So the main purpose of IR spectroscopy is to get the data about a functional group. We can identify the functional group by analyzing the IR data of a molecule. Now it is interesting to note that in every molecule there are many kind of bonds and all bonds vibrate, right? So for example, let's say you have a CH2 group. So this CH2 group can vibrate in different ways, like this CH bond can stretch like this, or it can also stretch like this. Okay, it can also stretch like this. So this one is called symmetric stretching and this one is called anti-symmetric stretching. Why it is symmetric? Because both hydrogens are stretching in this way, but in this case one hydrogen is compressing, another one is stretching. It is in general this mode is called stretching, but this one is symmetric stretching because both are stretching in the same way, whereas in the other case one is stretching, other one is compressing. So that's why it is anti-symmetric stretching. Other than stretching, there is another kind of vibration, and that is called bending. So this is called bending. Okay, what is bending? Now this CH bond, the same CH bond, it can move out of the plane, right? So one hydrogen can go above the plane, which we represent by plus, that it is go above the plane, and another can go below the plane, which we represent by minus. Similarly, both can together go above the plane or both can together go below the plane. Again, this is this one is symmetric bending and this one is anti-symmetric bending. So all these stretching and bending are there, and these we call the stretching frequency and bending frequency. So this is the inherent property of any bond, and all bond vibrates like this. So you can compare this vibration similar to that of a spring when it is attached to two balls like this. So you can compare these two balls with two atoms and this spring as a chemical bond. So the spring, if you vibrate, it will keep vibrating. Similarly, the bond vibrates. Now if you look carefully, a molecule composed of many bonds, and if all bonds vibrate together, the overall outcome will not be useful at all for any kind of analysis, right? Because you will get a overall picture, but it becomes helpful when you have a bond which the frequency of which is different from its neighbor. For example, if you have a carbonyl group and its neighboring groups are like CH groups, all are CH. Let's say we are talking about acetone, simple molecule acetone. So in acetone molecule we have 6 CH bonds and 2 CC bonds and 1 CO bond. Now if you compare the bond strength, this CO bond is different from all other bonds because it is much stronger than any other bonds, and that's why its stretching property or its vibration will be different from the others. And in the IR spectroscopy, if we have this kind of group which has stretching property are very much different from its neighbor, then it will be helpful to analyze that functional group with IR spectroscopy. So what are the factors that govern the stretching frequency or bending frequency of a molecule? So in general, the stretching frequency of a molecule depends on two factors, and that are the reduced mass of the atoms and the strength of the bond. So you can compare it with Hooke's law. So what is the Hooke's law? In Hooke's law, if we consider a vibration of a spring, Hooke's law tells that the frequency nu is equal to 1 by 2 pi c into root over f by mu, where f is the force constant of that spring, vibrating spring, and mu is the reduced mass of these two balls. In the chemical bond, we can apply the same concept. This force constant is roughly equal to the bond energy or bond strength, and this mu is the reduced mass of atoms which are there in the bond, right? So from this equation we can say that stretching frequency is proportional to the root over of f, that is root over of bond strength, or roughly we can say that the stretching frequency is proportional to the bond strength. That is, if bond is stronger, bond strong means stretching frequency will be high, and bond weak means stretching frequency will be low. Similarly, we can see that nu is inversely proportional to reduced mass. That is, if reduced mass is high, that is if you have heavier atom, then nu or stretching frequency will be low, and if reduced mass is low, then nu or stretching frequency will be high. So we can say that for strong bonds we will have high stretching frequency, for weak bond we will have low stretching frequency. Now at first hearing this may sound confusing to you, because you may think that if a bond is strong it will vibrate less efficiently. But think about one thing, that if you have a very sharp spring, or if you have a very rigid spring, and if you vibrate it, it will vibrate more frequently than if you have a loose spring, right? So similar logic you can apply to chemical bond. And what about reduced mass? So reduced mass is the most important thing, because it has more effect on the stretching frequency of a molecule, right? So for example, if you consider a simple CH bond, and if you consider a CC bond, and if you calculate the reduced mass of these two, in case of CH bond it will be around 0.92, whereas in case of CC bond it will be around 6, and if you consider CF bond it will be around 7.3 or something. So you can see, if you change carbon to fluorine, the change in reduced mass is very less, from 6 to only 7, but if you change it to hydrogen it is very low, that is 0.92. So that means whenever you consider a CH bond or NH bond or OH bond, in general we say it XH bond, where this X represents CN or oxygen. So this XH bond has very high stretching frequency. Why? Because it has very low reduced mass. So if you consider any bond with this XH bond will always have very high stretching frequency. So based on that we can classify our functional groups or our bonds in different categories or in different regions. So in the IR spectroscopy we have 4 major regions. What are that regions? So the first region is this XH bond, which is from around. So first of all we need to tell that what is the unit of measurement in the IR spectroscopy. So in the IR spectroscopy, this is a absorption spectroscopy, and what we do, we have a sample molecule. So we irradiate that sample molecule, or we pass our IR electromagnetic radiation, that is infrared electromagnetic radiation from infrared region to that sample, and some part of that light or that IR frequency is absorbed and some is released. So with the detector we detect that how much radiation is transmitted. So from that we can calculate how much is absorbed, and from that data we can say that what is going on inside the molecule. So now we can measure two things: either we can measure the frequency of the electromagnetic radiation, or we can measure the wavelength, and these two are in opposite direction because frequency is inversely proportional to wavelength. So what we generally measure is the wave number, that is nu, and nu is actually inverse of the wavelength, that is 1 by lambda is equal to mu, and this mu, in this mu unit we measure the frequency, the IR spectroscopy. So again we can see that this nu bar, this is actually nu bar. So this nu bar is proportional to nu, which is the frequency. That means if a molecule is the stretching of a molecule is high, that means if a molecule is vibrating at a higher stretching frequency, it will show a high nu bar value and low lambda value. That means a strong field region or a strong electromagnetic radiation region, right? So generally it is its unit is centimeter inverse. You can see because the lambda is taken in centimeter unit, so 1 by lambda will be in centimeter inverse. So the unit in which we express the IR data is centimeter inverse, and which is actually the wave number or 1 by lambda. Now what is the region which we observe? So in general for organic molecule we scan the region from 500 centimeter inverse to 4000 centimeter inverse. This is the region which we study, and of this big region we can classify into 4 categories. So the first category deals with XH bond. XH means all the CH, OH and NH. So this range is from 2500 to 4000 centimeter inverse. The second region is the triple bond region, that is CC triple bond and also CN triple bond, and it is from 2000, that means 2000 to 2500 centimeter inverse. This is the second region. The third region is the double bond region, that is CO double bond, CC double bond and all other double bonds, and it is from 1500 to 1900 centimeter inverse. And the fourth region is all the CX bonds, CX single bonds and also other single bonds. So this region means carbon halogen bonds, carbon carbon bonds, carbon oxygen bonds, all the single bonds, and this is from 500 to 1400 centimeter inverse, and all these are stretching frequency data. So these are the 4 major regions which we can classify based on the strength of different functional groups. Now we will study one by one each of these regions. So first let us talk about the XH region. So in the XH region we have 3 bonds: the CH bond, the NH bond and the OH bond. So first let us talk about the CH bond. Now we first showed that for all these hydrogen is there, and because of that the reduced mass of all this group is very low and they vary very little. So the first one CH is around 0.92, NH is around 0.93 and OH is around 0.94, and you can see this reduced mass difference is nothing. So that means reduced mass has no effect on the stretching frequency of these 3 groups. According to the reduced mass, all should come in the same frequency, but there is a difference in this bond strength. So CH, NH and OH, they differ in the bond strengths, and that's why you will see that CH bond they generally come at around 3000 centimeter inverse. The NH bond it comes around 3300 centimeter inverse, and OH it comes around 3600 centimeter inverse. Okay, 3600, so it is even higher. So this is the typical region for all these groups. Now if you consider a typical CH2 group or a CH3 group, it will come at around 2950 centimeter inverse, and this is a typical region, you should remember it. This is for CH2 and CH3. The situation for NH is even more interesting. The NH group, you can have NH2, either NH2 or you can have NH, that is secondary or primary amine, two amines. And in case of this secondary amine, you will have a very sharp peak like this, and this is at around 3300 centimeter inverse, and this is a sharp peak, singlet sharp peak. So what is mean by a sharp peak and what is mean by a strong peak, weak peak, that I will discuss later. I will use this term weak band, strong band, all these things, but what is mean by that I will discuss in a moment. So for NH we have this peak at 3300, but for NH2 we have two peaks like this, and one is at around 3400 centimeter inverse, and another one is at 3300 centimeter inverse. Now why this is the difference? For NH we have only one, for NH2 why we have two peaks? So how many number of peaks we will get, whether a singlet or multiplet, that is dependent on how many same type of functional group or how many same type of bonds are there which are connected. For example, in this case NH group we have only one NH bond, other are NR bond, so this NH bond is different from all other bonds around it. But for NH2 group we have two NH groups, and that's why here the interesting thing occurs. So this NH2 NH group, they will couple, the stretching frequency of them will couple. So we already showed that either they can have symmetric stretching or they can have anti-symmetric stretching like this. And for this anti-symmetric stretching, generally it requires high energy. So for this anti-symmetric stretching, it will come at 3400 centimeter inverse. For this symmetric stretching, it will come at 3300 centimeter inverse. So whenever you have this kind of bond, you will see that you will have a multiplet, doublet or anything like that. But when you have only one kind of bond, you will have always have the singlet. So this is for the NH region. Now the situation for OH is even more interesting. So I have said that for OH you will have a strong band at around 3600 centimeter inverse, but this is not the case always. Generally OH shows a broad peak from at around, so this range is from 33,000 to 3300 to 2900 centimeter inverse. This is a broad peak. This sharp peak you get, but generally you get this broad peak. So it depends on the extent of hydrogen bonding. You know that OH bonds are capable of hydrogen bonding, and if you have very simple molecule, I will discuss that alcohol. If you have alcohol, so alcohol molecules do hydrogen bonding between one molecule with another, right? So like this. So this hydrogen bonding, what it will do, due to this hydrogen bonding, oxygen is giving electron to this hydrogen center, and that's why this bond is weakened. This bond is weakened. So due to the hydrogen bond formation, this bond is weakened, and that's why its stretching frequency will be reduced. So from 3600 centimeter inverse, it will shift to the 3300 centimeter inverse, because due to the hydrogen bonding, this bond is weakened. Now why the broadening? We know that for weakening of the OH bond, this bond shift is there, this stretching frequency range shift is there, but the question is why this broadening of the peak? The broadening is because if you consider hydrogen bonding in a system, all hydrogen bonds are not same, so there will be a large number of hydrogen bonding, Avogadro number of hydrogen bonding, and all this hydrogen bonding differ in energy from one to another. So we will have an average value, and whenever we have an average value, it will be a broad peak. So because of the averaging of the hydrogen bonding, we will have a broad peak. So by looking at the peak, whether it is a sharp peak or it is a broad peak, we can say whether the molecule is involved in hydrogen bonding or not. One very interesting example we can show is, let's say you have paracetamol molecule. you have paracetamol molecule which is para-acetyl aminophenol, that is NH, and you have this NH, and you have this Ma, and here you have this OH. Now you will see that this molecule, it will have hydrogen bonding like this, intermolecular hydrogen bonding. Here you have this NH COMe group. So there will be intermolecular hydrogen bonding between two molecules, and you will see that broadening in the OH region. So you will see a broad peak at around 3300 centimeter inverse. Now don't be confused that then how we will recognize this NH group. We can recognize this NH group because this NH group will come as a sharp peak. So we can easily recognize this NH group, but at the same time for this hydrogen bonding interaction there will be a broad peak for the OH. Now if you consider another molecule where there is no chance of hydrogen bonding, this is called BHT. So you have two tert butyl groups over here, and you have one hydrogen, I mean OH group. Now the two molecules of BHT cannot come closer. Why? Because of the repulsion from this tert butyl group. So this OH group cannot participate in hydrogen bonding with this. There is no hydrogen bonding because of this large tert butyl group, and in this BHT molecule you will see that a sharp peak at around 3600 centimeter inverse. So by looking at the structure or nature of the spectra, you can tell whether hydrogen bonding is involved or not, right? So this is the XH region. Now we can summarize the XH region by a very nice picture. So this is the 3600 centimeter inverse region. This is for the non hydrogen bonded OH, and for hydrogen bonded OH you will have a broad peak like this, which is at around 3300 centimeter inverse. This is for hydrogen bonded OH. For NH group you will have a peak at around here. Okay, for NH2 group you will have two peaks like this. This is for NH2 group, and for the CH you will have these peaks around here, and these are for CH. This is around 3000 centimeter inverse. So this is for NH2, and this one is for NH. So this is the region, and another one which I didn't explain, I will do that. So this is at around here, which is at 3300 centimeter inverse. This is for alkyne CH bond. So when you have alkyne CH bond like this, it will come here. So this is very interesting. If you consider normal CH bond, it will come at around 300 centimeter inverse, but if you have alkyne CH bond, when the hydrogen is attached to a sp center, it will come at around 3300 centimeter inverse. Okay, why? Because reduced mass is same, but here you are increasing the bond strength. When you have normal CH bond with saturated carbon, what happens? It is like weak bond because it involves the sp3 hybrid of the carbon, but when you have the alkyne CH bond, it involves the sp carbon, and that's why the bond strength increases, and it comes at the same place where NH group comes. So this is the summary of the region XH region, and this region is not that much helpful in analyzing IR data because you know CH bonds are in every organic molecule. So the most interesting part of the IR spectroscopy is the double bond region, but before that let us discuss briefly about the triple bond region, that is the CN and the CC, these two bonds. Let us discuss this. So what happens for these two bonds? So these two bonds, they come from around 2000 to 2500 centimeter inverse, and you can see the reduced mass for these two groups will be almost same, only difference is there in the bond strength, and CN bond is stronger than CC bond. So you can guess that CN bond will come at around 2500 2000 at around, it is not exact, but 2200 centimeter inverse, and for the CC triple bond it will be around 2100 or less than that centimeter inverse, and this group is not that much important for the IR data analysis. So now we will enter into the most important region, and that is the double bond region, the CX double bond, that is CO and CC double bond. So in this case we have the most interesting and important functional group which is analyzed by the IR spectroscopy, and that is the carbonyl group. So carbonyl groups are the most important group which is analyzed by the IR spectroscopy, and there are several type of carbonyl groups. They vary in their bond strength, and that's why you will have a range from 1500 to 1900 centimeter inverse. This is the region for the carbonyl functional group. For the CC double bond it comes at around 1600 centimeter inverse, and you will see that this CO stretching, this is strong, this is a strong band, this shows strong band and sharp band, whereas this CC they shows weak, this stretching they shows weak band. So in the structure you can see that for CO you will have these kind of big peaks, but for CC you will have this small kind of peak. Now why this strength difference is there in the stretching frequency of the band structure, that I will discuss within a moment. So CO bond comes at around 1600 centimeter inverse, that is the region for CC, for CC alkene region, and for CO it varies. Now CO is very important functional group, and in the next part of IR spectroscopy I will discuss the CO functional group in detail. Here I am just putting few examples. For example, this acid group, carboxylic acid, it comes at around 1720 centimeter inverse. This simple ketone, it comes at around 1710 centimeter inverse, and another group is there, amide, this NH2 amide, it comes at around 1667 centimeter inverse. So you can see, depending on the electronic nature of this carbonyl group, whether NH2 group is attached or OH, or whether simple alkyl group, the stretching frequencies varies dramatically, and this needs some a big discussion, detailed discussion. So that's why I will discuss them in the next video. But for now you just know that it varies depending on the nature of the functional group. So this is the double bond region which is most important for us. Now let us talk about the third region, that is the XX bond or CX bond, that is the single bond, the single bonds other than XH single bonds like C halogen bond or CC bond or CO single bond, all these things. So here the CO is the bond which comes at the highest stretching frequency value, and it is at around 1100 centimeter inverse, and in general this region falls from 500 to 1400 centimeter inverse, and this region is not that much helpful because there are a lot of stretching frequency values in this region, and also the bending values are also come, which is also called deformation, that is this type of movement of the molecule like this, and out of the plane, all this movement, the bending, this is also called deformation. So like you are bending a rod like that. So these values comes at around, for example, for CH2 group, the bending, CH2 bend or deformation, we can also show it by DEF, deformation, it comes at around 1470 centimeter inverse. The CH3 def, it comes at around 1780 centimeter inverse, and NH2 def, it comes at around 1550 to 1650 centimeter inverse. So this is the bending region. So all this 500 to 1400, this is a messed up region. There are a lot of frequency values. one interesting value here is the CCl bond. For it there is a peak at 700 centimeter inverse, and this is a characteristic peak. So by analyzing this peak we can say whether a CCl bond is there or not. So this is the region which is called the fingerprint region. Why? Because for this region you cannot characterize one particular functional group like that, but you can characterize the whole region as a whole like this. So this region actually looks like this. Okay, so you can overlap. So you take a data, you have previous experimental data of the same region, you overlap these two, and then you can say that yes, this is this functional group or this is this molecule. So you can characterize the overall molecule. Like human being, we have different fingerprints for different human being. Similarly, for different molecules, this fingerprint region is different, and this is called the fingerprint region. So you cannot characterize one particular functional group in this region, but you can characterize the molecule as a whole by overlapping of this region. So that's why it is called the fingerprint region. So this is the overall picture of the IR spectroscopy. Now let us talk about the strength of the frequency or the intensity of the frequency. That is, we talked about the term strong and weak, all these things. So what is mean by a weak band and what is mean by a strong band? So you will see in the IR spectra there is some bands which are like this, very sharp and big, whereas some bands are there like this. And if you just consider two simple case, for example CO double bond and CC double bond. So this weak peak or weak band is represented by this CC double bond, whereas this strong peak is represented by this CO double bond. Now why CC peak is weak and CO peak is strong? So the strength of this peak band structure depend on one factor, and that is the intensity of the absorbed light. How much absorbed light is how much light or how much electromagnetic wave is absorbed by the molecule, and that in turn depend on the change in dipole moment of the molecule. Yes, so this change in dipole moment is very important. If a molecule doesn't show any change in its dipole moment through its bending or stretching, it will not be active at all in the IR spectroscopy. So first condition of a molecule to be active in IR, it should change its dipole moment through stretching or bending. Now if you consider a carbonyl group and simple alkene, you will see carbonyl group is inherently polar because oxygen is more electronegative than carbon. So that's why there is an inherent dipole moment, and through its bending or any other stretching it will change its dipole moment. So that's why it is more IR active and it will absorb more electromagnetic radiation, whereas this CC group, this is inherently non-polar, and when some group is there, then some polarity is introduced in the molecule. But if you compare the polarity difference between these two, carbonyl and the alkene, you will see that there is a hell and heaven difference. That carbonyl is very much polar and this carbon double bond is very less polar, and because of this low polarity there is a low polarity change in the stretching also, and this in turn reflect in the structure of its structure of this band. Okay, so because it shows low polarity change, low dipole moment change through stretching, it has weak peak in the IR spectroscopy. Similarly, if you consider a CH bond and OH bond or NH bond, you will see that nitrogen and oxygen, they are more electronegative, and that's why this OH and NH bond, they are much more polar compared to a CH bond, and that's why you will see weak band at 3000 region which are for this CH group, whereas a strong band at 3600 or 3300 centimeter inverse which are for OH and NH bond. So the strength of band depends on the change in dipole moment of the molecule through its stretching. So this is the thing. So now we can summarize all these things. So the strength of band, strength of band depends on change in dipole moment, that is the polarity of the bond. polarity of bond, okay, and the region in the spectra depends on two things. One is reduced mass and another one is bond strength, okay. So this is the summary. And also what is the effect of hydrogen bonding on OH? So the effect of hydrogen bonding is that if you have hydrogen bonding, you will have a broad peak and lower stretching frequency. If you don't have hydrogen bond, you will have strong peak and at higher stretching frequency. So here I will stop today's video. In the next video I will discuss this carbonyl functionality in detail, when all the different functional groups are there as a form of X, like amide, carboxylic acid, ester, all these things. And also I will discuss the effect of hydrogen bonding, intra and intermolecular hydrogen bonding, and related questions. So basically the next video will be more helpful for exams because I will discuss questions. So if you are new in this channel, subscribe this channel, watch this series on spectroscopy because I am making this video on your request, okay. So that's all. Thank you for watching.